Hey guys, in this lesson we're going to be discussing the differences between exponential growth and exponential decay. So by the end of this lesson you should be able to solve problems that involve both exponential growth and exponential decay. Now we know that the basic equation for all exponential functions is going to be y equals a times b dx, where a represents the y-intercept and b is going to represent our growth or decay factor. We know that the graph for all exponential growths is going to increase gradually and then all of a sudden explode into these higher values, such as this graph that we have right here. In exponential decay, our values are decreasing rather quickly, but then they gradually begin to slow down. And so we know that the differences between our graphs is gonna be one where our curve is going up and one where our curve is going down, or the other direction. Now, we're going to be moving more into real-world situations as we dive into exponential growth versus decay in today's lesson. And so one thing that we need to talk about is that oftentimes in real-world situations, we're not given the growth or decay factor, but instead we're given the growth or decay rate. So if we want to get the growth factor, when we're given the growth rate, we would take that percentage rate, we would change it to a decimal, and we would add it to 1. So we would do 1 plus that percent as a decimal. And to get the decay rate, we would do the same thing, but instead of adding it to 1, we would subtract it from 1. So we would take that percentage that they give us, we would change it to a decimal, and we would subtract it from 1. That way we have that growth or decay factor. It's important that you do this when we're dealing with real world situations, because if you mistake the growth rate for the growth factor, you're going to end up with two completely different answers. Now, our equation for exponential growth when we're dealing with the rate is going to be y equals c, parentheses 1 plus r to the t. Remember that we're going to add that rate to 1. Y is going to be our final amount, so we're not going to have to do anything special with this after we're done. So after we plug in all of our values, we'll end up with our final amount. C is going to be the initial amount. That's going to be the y-intercept. That's the amount that we're starting with. R is going to be the rate of growth. Remember, we're going to change that percentage rate to a decimal, and we're going to add it to 1. And then t, our exponent, is going to be the time. So it could be number of years, could be minutes, could be whatever that time length is. And then for the decay, it's going to be the same thing that we're looking at for growth, except instead of plus r, we're going to see minus r. So again, we're still going to have y as the final amount, c is going to be our initial amount, our y-intercept, r is going to be the decay rate this time as a decimal, and then we have t is the time, again, that's going to be our exponent. So let's look at this first example here. So here we have a gym currently has 2,000 members, and it expects to grow at 12% every year, or per year. How many members will it have in 6 years? So 2,000 members is our starting amount. So A, our y-intercept, is going to be 2,000. The growth rate per year is 12%. We'll change that to a decimal. That would be 0.12. And so B is going to be 1 plus 0.12, or 1.12. So remember that to get B, we're adding that percentage rate as a decimal to 1 when we're talking about a growth. We know that this is an exponential growth because it expects to grow, and so that's how we need to add it to 1. The desired time period is 6 years, so x is going to be 6, since we're looking at 6 years. And so we substitute all of those values into our equation, and so our equation is going to be 2,000a times b, which is 1.12 to the x. And so then we can substitute those values into now we can solve this. So now that we know that x is 6, we can substitute that in for x. So we have 2,000 times 1.12 to the power of 6. When we raise 1.12 to the power of 6, we get about 1.974 if we round it to the thousandths place. And then when we multiply that to 2,000, we get 3,948. So in 6 years, this gym can expect to have 3,948 members. Now let's look at this next problem. So here we have in 1971, there were 294,105 females participating in high school sports. Since then, the number has increased an average of 8.5% a year. Again, that word increased lets me know that this is going to be an exponential growth. How many female students participated in sports in the year 2001? So we want to write the equation to represent this situation. Well, again, our y-intercept here is going to be 294,105, since that is our initial amount. Our rate is 8.5%, so as a decimal that would be 0.085. and we would add that to 1 because we're given the rate, so we want the factor, so we'd add that to 1. And once we do that, we get 294,105 times 1.085 to the power of t. Now we want to calculate t. So we're not given the number of years. We just want to know how many females participated in high school sports in 2001. So to get the number of years that have passed between 2001 and 1971, we would subtract those, and that would give us 30 years. And so therefore t would be 30. Now that we know that t is 30, we can substitute that into in for t in our equation, and we can solve for y. So when we do that, we get 294,105 times 1.085 to the 30th power. When we simplify that, we get 11.558 times 294,105. And when we multiply those together, we get 3,399,265 females were participating in sports in 2001. And so once we have those values, we can substitute those in, and from that point, it's fairly simple. Let's look at this final example here. So here we have in 1950, the use of coal by residential and commercial users was 114.6 million tons. Many businesses now use cleaner sources of energy. As a result, the use of coal has decreased by 6.6% per year. And so we see that this is an exponential decay since the use is decreasing. Estimate the amount of coal that will be used in 2015. And so again, we want to write our equation here. So we're going to start off with y equals c, parentheses 1 minus r to the t, since this is our equation for exponential decay. We're going to substitute in our values. So c, our initial value, would be 114.6 million tons times 1 minus 0.066, since 6.6% as a decimal would be that, to the power of t, since we don't know how many years we're looking at just yet. We're going to go ahead and simplify this parentheses part, and that's going to give us 114.6 times 0.934 to the power of t. Now we want to calculate t. So the same thing that we did before. We don't know how many years have passed between 1950 and 2015. So in order to figure that out, we want to subtract, and we get 65. And so therefore t is 65. So we can substitute that into our equation. When we do that, we get 114.6 times 0.0118. And when we multiply those values, we get 1.35228. Remember that this is in million tons, so in 2015, there was about 1.35 million tons of coal being used for commercial and residential properties. Okay, so these are the differences between exponential growth and decay, and this is how we solve problems with exponential growth and exponential decay.